Okay, so Dr. Cinco talked about center of mass enough, I think, so I'm going to skip that. And the biggest thing here is to talk about the moment of inertia and talk about the fact that in rotating objects, it's going to be more, well, not more, but it's going to be as important to consider mass, or where that mass is distributed, as mass itself. So when we talk about moments of inertia, those formulas come from where the mass or how the mass is distributed. And we're going to look at Newton's second law for rotating objects and substitute in torque for force and moment of inertia for mass, which is, of course, mass and how it's distributed, and then alpha, or angular acceleration for A. It looks like these did not come across correctly. So that's torque. Those Greek letters, I guess, just don't, they don't do so well. This is actually torque, and this is alpha. And so when we summed up those and we integrated, that's what that looked like. And I think Dr. Cinco went through how we calculated with a moment of inertia for a long object of uniform mass circulating from the axis point. So I'm pretty sure he went through that with every class. But when you get lots of different formulas, these are some pretty typical formulas, and we're going to be using those. You obviously can calculate your own if you'd like, but I think for the most part they're the ones we're going to be using. And if you're ever in doubt which ones to use, just ask me. Sometimes it's obvious, sometimes it's not. Okay, so realizing that the farther the mass is away from the center of rotation, the more rotational inertia something's going to have is an important concept. So this one I think is a really good one. We did this one in class. The tightrope walker, or even just if you want to walk in a straight line, you put your arms out to the side. That distributes your mass farther from the center of rotation, and so you have more rotational inertia. You're less likely to rotate. Now, if you want less rotational inertia, like you want to go fast, you're going to make those that mass closer to your center of rotation, so that's why a person will run with their legs bent, not straight. A pendulum swings faster than a long one, a short one, because that mass is closer, so less rotational inertia. And I think Dr. Cinco talked about that one. Okay, so Newton's second law is force is equal to mass times acceleration. So a force with a lever arm is going to be a torque. A mass with how it's distributed will be a moment of inertia. And rotational acceleration alpha will be for A. And so again, choose a moment of inertia. The list is pretty much going to be everything we have. You can have obviously very, very complicated moments of inertia. Just for fun, look up a moment of inertia, how to calculate the moment of inertia for a bowling ball. It's kind of interesting. Okay, so a couple of examples here. We have a catapult arm. So I'm thinking, if you have a catapult, this is probably not going to be, now, I'm going to do a point mass about an axis, because the arm of the catapult, is not going to be much of anything compared to the end of it. So I'm going to choose the point mass about an axis. So we have a moment of inertia that's going to be mr squared. So the mass at the end will be this 150 kilogram stone, the radius 0.35 meters. That's actually a very tiny little catapult. And the moment of inertia is going to be 0.018 kilogram meter squared. All right, the tangential acceleration is 100 meters per second squared. But of course, we remember how to get the alpha. We just multiply by r. So alpha then is going to be 100 divided by 0.35. Wow. And we're going to get 286 radians per second squared. And so then our torque is going to be moment of inertia times alpha. And so we're going to get 0.018 times 286. and we will get a torque of 5.14 Newton meters. For the next one, we have a hoop, and if you look back at the page of moments of inertia, that too will calculate to be mr squared. And so the mass is 0.165, and what is alpha? Well, alpha, we're going to have to maybe go back to our angular kinematics occasionally. It won't be anything too bad, but we might have to go back to find our alpha. So it started at 30 radians per second, and it takes 0.10 seconds to stop it. So we're looking at negative 300 radians per second squared. Our moment of inertia, like I said, is going to be mr squared, so we're going to go 0.165 kilograms times a radius of 0.135 meters. Yeah, it has to be in kilograms and meters so we can get newtons and that kind of thing. So we are going to have a moment of inertia of 0.003 kilograms meters squared. Our torque then is going to be moment of inertia times alpha. We're going to get negative 300 times 0.003, and that will give us negative 0.900 kilogram meters squared. The force exerted on the hoop, that'll be our force. So we know our lever arm is the radius, so we're going to go force times lever arm, which is just the radius. And we're going to set that equal to the torque, because we are going to use both of these because they're both equal to torque, so we might as well use them. And we're going to get a force equal to negative 6.7 newtons. 6.7 newtons. Oh, and also, I am not going to do the next example. We just really don't have time if we're going to get a test in before spring break. So 40 and 41 of your homework, you can try them if you want to try them, and I can certainly show you how to do them. They're two free body diagrams. Do a free body diagram and calculation for the spool, and do a free body diagram and calculation on the block that's attached to the string. And between those two free body diagrams, you're going to have an acceleration that's the same, and you'll have a tension that's the same, and you'll have two different sets of calculations. So you don't have to do 40 and 41, but if you're interested, I can show you on Monday.